The afternoon and final session. The first speaker is Professor Veraar from Technical Institute. He is going to speak about stochastic maximal LPA.
Yes, that's right. Thank you very much for the opportunity to give here a talk about what I'm working on at the moment. I'll write the title down again. The talk. It's stochastic maximal LP regularity. And this is joint work with Jan van Nerven and also with Lutz Weiss. And actually we have been working on this subject for, well, a long time already. It was a difficult problem, but we made some nice steps. A less modest title of the talk would be something like Krylov's LP theory for a large class of operators. I will explain a first important step in trying to get an LP theory for a larger class of operators than Krylov has. Some of you might know this theory. If you don't know it, it's no problem. I will explain a bit about it. And of course, it's an important question to wonder why we want to consider LP, because L2 is so nice. But there are actually many reasons for it, but the most important reason to consider LP is the application to nonlinear equations. In deterministic PDEs, often LP methods are used in order to treat nonlinear equations. And why is that possible? That's because of Sobolev embeddings. Especially if P is large, then Sobolev embeddings work really nicely and you get a lot of integrability from your regularity. So that's my motivation why I'm so interested in LP theory. And what I will do today is explain the first step of the theory and the applications to SPDEs. I will not do in the talk today because it would be too much. And I want to explain a bit about the techniques. I will not give many proofs, but I want to explain techniques. So let me give a rather long introduction. On the subject. So this will be part 1. And during the talk, I will have two numbers, P and Q, and for most of the time, P and Q are between 2 and infinity. So if I write something with a P and a Q and I don't say what it is, then it's probably between 2 and infinity. X will be an LQ space over a measure space O with, well, it doesn't really matter. I will assume that it's a sigma finite measure space. And it could also be, X could also be isomorphic to a closed subspace of LQ. Everything I will say during the talk will also work for X being isomorphic to a closed subspace of LQ. So Sobolev spaces, etc. That also works. And also A will be the generator of an analytic semigroup and I will assume that it is exponentially stable. Semigroup, and I will call the semigroup S of t for t greater or equal than 0. And this will be on my space X, okay? This will be on my space X. Okay, and well, furthermore, we have, of course, a probability space which will be filtered. It will be rich, a rich probability space. Filtered probability space. And on this probability space, I will consider a Brownian motion, a standard real-valued Brownian motion. But I should say that what I will tell today is also true for cylindrical Brownian motions. That doesn't really matter, but it makes the talk more complicated, and I want to keep it easy. So I will just consider standard real-valued Brownian motions. And there will be an equation that will play a crucial role, and it's a really easy equation. I will call it equation 1. It's this equation. And what is not said yet, I did not say what G is, of course. I did not say what G is. So G is in this equation just a process which takes values in X. And it will be adapted and measurable. And well, this is a really easy equation, I agree. So I'm not saying that, that this is the most important equation to study, but it is, for many equations, a good beginning to start, to understand this equation. And since I'm interested in maximal regularity estimates, I will just solve this equation, but that's not the big deal. The big deal is to get as much regularity as you can. So I will prove a maximal regularity result. Much is known about regularity for deterministic equations, but not so much is known for maximal regularity for stochastic equations. But I will come to the references that are available in a minute. Well, let's solve the equation. That's not easy, not hard, but I mean. So the solution is given by U of t is this stochastic integral. But be careful, I'm working in a Banach space, so I should say what I mean with this stochastic integral. So let me do a small intermezzo for the stochastic integration theory. And actually there will be two intermezzos. So the first one is on stochastic integration theory in M-type 2 Banach spaces. well, I will not explain the full M-type 2 stochastic integral, but I will focus on the case of LQ with Q greater or equal than 2. So that's what I immediately do, but you can do much more. But this is, I just want to make a point. And this theory is used a lot, and the one that uses it most is, I think, Bozesniak, and also many of his co-authors. And it's a really nice theory. It's a nice theory. What is the theory based on? It's based on the following estimate. For all p bigger than 1, there exists a positive constant such that for all processes g mapping from r plus times omega with values in x, measurable and adapted, we have the following estimate. What is the estimate? Let's call it 2. This estimate was actually already in the talk by Annie Millet, but I will write it again because it's slightly different. And probably the audience doesn't, at least all of them probably don't all remember. So this is the one side of the estimate, and the other side is c to the power p, and then here the expectation of the L2 norm over r plus with values in x to the power p. Like this. So this is their estimate. Yeah, sorry. Thank you. It should be G. Okay, and so usually this is called a Burkholder-Davis-Gundy inequality. And why is it useful? Well, I mean, you can integrate a lot of things. You can integrate as soon as you have something like paths in L2. You can integrate functions. And the only difference with the Hilbert space theory or the real value theory is that you only have an estimate. It's the only difference. You just have an estimate and not an equality or a similarity in norms. So that's the difference. So let's see what this theory gives us now for this guy here. So let's try to do an estimate. So what do I want to estimate? I want to estimate the expectation of minus a to the power delta, and I do this for delta positive. Is there a question? Okay. So I will try to estimate this to the power p. Why not? So I don't need really this supremum now. It's not such a big deal for me now because I have a convolution, so I cannot use that anyway. But what I can use is the inequality without the supremum. So let's see what this gives. So this is actually integral from 0 to t minus a to the power delta s t minus s gs dw s to the power p. And now we can use the inequality. So what does the inequality give? The inequality gives that this is smaller or equal than a constant to the power p, and then I get minus a to the power delta s t minus s g of s, and this integrated from 0 to t to the power 2 ds. So that's the L2 norm, but then I still have an LP norm like this, and I get a p over 2 because of the L2 norm. And that's it. Well, what do you see? You see that this behaves more or less like t to the minus s, t minus s to the power minus delta. But I have a square here. So what can I do? This makes sense as long as delta is between 0 and 1/2. And what can I do in that case? I can estimate this with t minus s to the minus 2 delta, and then here the norm of g to the power 2 ds p over 2. Okay, and that's it. If delta is 1/2 or larger, then you have problems with this integral. But what you already see is that you have some sort of singular stochastic integral as soon as you put this power here. But so let's estimate now the LP norm of this guy. So what do we get if we estimate the LP norm in time now of this, what I started with? So that gives the expectation of, well, just let me write it in this way. What do I get? LP r plus omega with values in x of u, that will be, if you use the inequality that I just showed together with Young's inequality, using these two functions, then you will get that this is smaller or equal than some other constant, and then here g LP r plus times omega with values in x. That's then not difficult. And you use Young's inequality with exponent p over 2. So then you see already that p greater or equal than 2 is kind of important. And yeah, this is the estimate. And what I want to do now is I want to take delta equal to 1/2. I want to take delta equal to 1/2. But it's not possible. And except in one special case, except in the Hilbert space case. So if I take Q is 2, there was still some space X. If I take Q is 2 in this case, then there is an argument due to D'Aprato, and it's in the book, that you can still do such a thing. But you have to use properties of your operator A. But using this theory in the non-Hilbert space case, it doesn't work if you really want to have this operator. You can do other things with real interpolation spaces, for instance. So the message here is that delta is 1/2 is difficult with this theory. So what should we do? Is there hope? So let me make a definition. And what's my definition? That's part 2. The definition of stochastic maximal LP regularity. And what is this definition? It's a property of the operator A. So we say that A has maximal, or actually stochastic, maximal LP regularity if the following estimates hold. The following estimate holds. If there exists a constant greater or equal than 0, such that for all g in LP r plus times omega with values in x, and it has to be adapted, of course, we have the following estimate. that U, where U is now the same thing. Well, maybe I write it slightly different. So I want to have this norm of my solution U, so U is the same thing as I had here. And what kind of estimate do I want? I want to be able to estimate this with the LP norm of G. And there can be a constant here. Well, I mean, this is just a definition, doesn't say much yet, but if you would have such an estimate, this would help in SPDEs. You can do things for limiting cases. So, and what's also an important observation here is that if you calculate this LP norm, this will give a singular stochastic integral. You have to work with a singular stochastic integral. I mean, there's a lot known about singular integrals, but there's not so much known about stochastic singular integrals. And why would this be important to have this regularity in this space? Well, for second order operators, for second order differential operators, you usually have that d minus a to the power 1/2 is something like W1, and I was in LQ, so I get W1Q with boundary conditions. Yeah, I mean, there could be boundary conditions, and you usually get that. So, and this space would be quite nice to have this such regularity of your solution, right? Then you have one-time differentiability. So the main objective in the talk is to find out what's going on here. Do we have examples or not? And what kind of examples? So the main objective is which A have stochastic maximal LP regularity. And once again, the motivation comes from nonlinear SPDEs. So this brings me to the second intermezzo, and this is another stochastic integration theory. And now I have to get rid of something. Let's see. Well, maybe this calculation, we don't need it anymore. So the second intermezzo and what's this for kind of intermezzo? It's stochastic integration theory in UMD Banach spaces. In UMD Banach spaces, I will not explain what UMD Banach spaces are. We will just again focus on X's LQ. And now for the first time in the talk, we can take Q also below 2. That's not so important for the talk, but I want to write it anyway. And what is the theory? Well, the theory is from a paper by Jan van Nerve, myself, and Lutz Weiss, and this was in 2007 in the Annals of Probability, where we constructed such a theory for stochastic integrals for processes with values in UMD Banach spaces. But again, the important case for the talk is X is LQ. And what could we prove? We could prove that for all p bigger than 1, there exists a constant such that for all g from R plus times omega with values in x, and again adapted and also measurable, we have the following estimate. There actually exist two constants. I need two constants, one small c and one capital C. And what do we have? We have, and now it becomes a bit difficult, so I will cheat a bit. I will put a question mark here. And here's my constant c, and I have here my stochastic integral gs dws to the power p, and this I can estimate with c to the power p, again with the same thing. And again I put a question mark. So why am I cheating? I'm cheating because I will not explain what the question mark is. You can look that up in our paper. So what we did is this is some norm, and it's a norm over time. So if you throw in a function in this norm, then it gives you a number. So for functions you get some sort of norm. So what is the big deal of this paper? Well, we were able to find a norm which says something like this. So which gives estimates, two-sided estimates for stochastic integrals. And is it the right estimate? Yeah, of course it's the right estimate because it's two-sided. But the difficult thing now is that you have to get used to this norm. So it's not an easy norm, but after a while you really get used to it, and you can prove things with it. So so it's a bit stronger than this theory, even in the case where you take this space. Why is it stronger? Well, because we have a two-sided estimate. So it should also be true that if you take q bigger or equal than 2, that then we can estimate this over here by what we have over here. And that's actually true, something like that. And yeah, let me make some remarks about what we already know for kind of applications of this theory. This will be short, a short list that's somehow convincing. So first of all, it's not so important that this is a Brownian motion. You can take other processes as well. So for instance, you can take any continuous local martingale. So that's something that that you can do. So W replaced by some continuous local martingale M, that's possible, and that's actually in one of my papers. I forgot the year. It's something like 2008 or 2007 in stochastics. That was kind of a nice exercise to do. Try to see if that works. I must admit that non-continuous local martingales are more difficult to treat. So that's a whole different story, and some people are working on this. So what are the advantages of this theory? the advantages of this theory in Intermezzo 2. Well, the first one I already said, we have optimal estimates for stochastic integrals. And the second one is we have something like Ito's formula for the duality map. So for the duality map, what do I mean with that? Just the map that you have in the sense that LQ prime is the dual of LQ. And since Q prime is also between 1 and infinity, you have an Ito formula for such functions, and that can be really useful. For instance, in one paper that the three of us have together with Bozesniak, we applied the Ito's formula to this function, and using that we could generalize some Hilbert space results of D'Aprato and Tubero. And well, that's was also nice to find out how that works. And the third thing is you can solve. So we can consider stochastic equations in LQ with Q arbitrary between 1 and infinity. And this theory only can do Q larger or equal than 2. And is that important? Well, it can be important. I have, for instance, so this is treated, by the way, in the paper by the three of us in 2008 in the Journal of Functional Analysis. And but at that moment we didn't have good examples why you should need LQ with Q small, but now I found one, and this is a paper of me together with Roland Snaubelt, which is almost accepted. So that's probably will appear in 2010. And we consider some sort of damped plate equation with a Dirac perturbation. And for that we need the reverse thing of a Sobolev embedding, and then we need Q small. So that was kind of funny. It was actually somebody that tried to do it without much theory. So he tried to do it in Hilbert spaces, but it only worked for dimension 1. And we can do it for arbitrary dimension. That's kind of nice. So there's a fourth thing. So there's no room on that blackboard, so where shall I put that? Maybe over there, yeah. So the fourth thing, and that's actually not my work, that's a paper of Jan van Nerve and Jan Maas. Well, it should be the other way around. And what did they show? They proved that you have something like a Clark-O'Connor formula. In this space, in this Banach space X. And actually they made the start of giving a whole Maillard-Vin calculus on Banach spaces, which is of course quite natural to ask if such a thing can be done. And such a Clark-O'Connor formula you cannot get with this theory because you only have one estimate. Now, and hopefully I can give another motivation today of this theory, because what I will try to do, I will try to show you that the theory of this Intermezzo 2 is strong enough to answer the question maximal LP regularity. So that's what I will try to show. But before I do that, I must say, I must show you what is already known, otherwise it doesn't make sense. So let's see. This we don't need. So of course I have to explain you what is already known on maximal regularity. And there are basically three things. And the three things are, if X is a Hilbert space, then and P is 2, then it was a result of Prato from 82, I think. And what did he show? He showed that if d minus a to the power 1/2 is equal to the real interpolation space at smoothness and a half and index 2, if you don't know what it is, it doesn't matter, but if you know what it is, it helps a little bit to understand the talk. Then A has stochastic maximal L2 regularity. So that's something you can show. And this assumption is fulfilled for many operators A, but not for all. So this is really an assumption on an analytic semigroup. So there are examples where you don't have that and where you don't have stochastic maximal L2 regularity. But for most elliptic differential operators, we know that such things hold. And the second one is X is LP on RD and A is the Laplacian on RD, so no boundary conditions. And Krylov in 94 proved stochastic maximal LP regularity. That's something that he could show, and that's the basic estimate in his LP theory. I mean, his LP theory wouldn't work without this estimate. And the proof is kind of hard. I think he would also say himself that the proof is pretty tough. A lot of harmonic analysis is going on, and it runs through several pages, a couple of 10 I would guess. And it's based on Fourier analysis. I mean, you have this nice RD here, so he can use Fourier analysis. So his proof does not work on bounded domains with, for instance, Dirichlet boundary conditions, which is of course also a nice operator. And the third thing that exists is regularity in the real interpolation scale. The real interpolation scale. So, who did this? This was started by Posesniak in 95, and after that also Prato and Lunardi have a nice paper on this. But it's on the real interpolation scale. So in the end, if you work with the real interpolation scale, you will not get these nice spaces, but you will get Bezoff spaces. And you will need also that your G is in some sort of Bezoff space instead of an LQ space. So that's, well, it's nice, but I would prefer the LQ spaces. It's just easier to work with in applications. Okay, let's see. Yeah, so it's maybe important to say that these results do not extend. So the proofs of these results do not extend to my general definition. So we were kind of stuck for a long time, and we tried all these techniques, and we thought our theory is strong enough to do such a thing, but it didn't work for a long time. But then we worked really hard, and we had some new ideas this year, and now things get going. So let me just state the main result, and in the next paragraph. Okay. So if I say our recent progress, then I mean again with Jan van Nerven and Lutz Weiss. And this is still a preprint, but I do expect that the paper will be submitted by the end of this month. So again, I take X is LQ with Q between 2 and infinity. And let me just state the theorem. But we still need something in the theorem that I did not explain yet, but I will do that after the theorem. So this is theorem 1. And this is what I did not explain yet, condition H. So if H holds, I will come to that in a minute, then A has, then for all P between 2 and infinity, A has stochastic maximal LP regularity. But be careful, I do not allow P to be 2 for the moment. So what does this mean? Let me write out the estimate to be complete. There exists a constant greater than 0, such that for all G we have the following estimate. Yeah, I want to write it out again because there will be a similar statement later on. So this is the theorem. So this theorem in principle answers the question, except that I did not explain condition H yet. So let me do that now.
Could you repeat the H or what this is?
I will explain now what H is, yeah. Okay, so condition H what is it? Well, it has to do with functional calculus. It has to do with functional calculus. And what kind of functional calculus? It is something related to the H infinity calculus. The H infinity calculus. H infinity calculus is a really popular subject for the last 20 years, I would say. So this is something that was invented by Macintosh, who's an expert in harmonic analysis. I think in the 80s, I think it was something like 85 or 86. I'm not sure about that. And it's some sort of extension. It's an extension of the calculus, the functional calculus for self-adjoint operators on Hilbert spaces. But this extension also works on Banach spaces. And what do I need? I will need that minus h has a bounded H infinity calculus of angle smaller than pi over 2. So that means more or less that I can give a meaning. I can give a meaning to things like f of a for f holomorphic and bounded on some sector that should be related to the angle that I have in condition H. So as soon as you have that f is holomorphic and bounded on a sector which is strictly larger than something to do with A, then I can give a meaning to this. And I want to have estimates like this with a uniform constant. So that's more or less what the H infinity calculus is. I mean, I'm not really precise now, but that's a whole other talk that would be just functional analysis explaining this. But what is the nice thing? The rule of thumb that one has is that all elliptic differential operators on LQ have satisfy condition H. Satisfy condition H. So all the operators you usually work with satisfy this condition. You just need a little bit of regularity on, for instance, your coefficients in your second order operator or your higher order operator. So let me state a few examples. I don't want to make a really long list, but I mean, people are really working on these examples for now, I think 20 years or something like that. And there's really a whole industry around that. So second order operators with smooth coefficients are shown to have this property in divergence form or non-divergence form, doesn't really matter. And what examples did I still want to write? Yes, there's one abstract example. So an abstract example is if ST is positive, is a positive contraction, then H holds and H holds. And in the Hilbert space situation, this condition H is exactly equivalent to, do I still have it? Yes. In the Hilbert space case, the boundedness of the H infinity calculus, so this condition H is exactly equivalent to the equality that D'Aprato assumed. So that's also kind of nice. So in that sense, it's a natural generalization. Well, what more do we have? We, for instance, have Stokes operator arising in Navier-Stokes equations, and which is nice because then you can do things for Navier-Stokes equations, especially stochastic Navier-Stokes equations with multiplicative noise, but also for Schrödinger operators. Schrödinger operators also satisfy this condition H. So this theorem is applicable to really a lot of cases. Most cases you have in applications. Well, there's a second theorem, which is also which I also really like. So again, I assume H. Then you have for all p between 2 and infinity that, so what is the estimate in this case? The expectation of the supremum t greater or equal than 0 of u of t to the power t, and now with values in this real interpolation space is smaller or equal than c to the power p. And again, the same norm of g as before. The same norm of g as before. So this space is also in some sense maximal. You cannot do better than this space. And it's a really nice space. People usually call the space of continuous functions with values in this guy something like the maximal regularity space. They call it that way in deterministic equations. And for stochastic equations, you have this guy here. Okay, so a few questions and a few answers. First of all, if Q is 2, then P is 2 is allowed. So I did not allow P to be 2, but if Q is 2, then it's okay. So we still cover the Hilbert space framework. And yeah. The result for Q is 2 is also nu for P bigger than 2. So I don't think that anybody ever in the Hilbert space case proved stochastic maximal LP regularity with P different from 2. So that's also quite interesting that that's really new. But more importantly, if we take Q bigger than 2, or Q greater or equal than 2, and P bigger than 2, and we take A is the Laplacian on LP RD, or LQ RD I mean, we get a generalization of Krylov result. So even in the setting of RD that Krylov considered, we can generalize his result because we do not have to take P and Q equal. We can just take any P and any Q. So that's kind of fun. But moreover, we can also take A to be the Laplacian on a regular domain with, for instance, Dirichlet boundary conditions. With Dirichlet boundary conditions, which is kind of fun. Now, I still have a couple of minutes. I don't want to say much more, but I want to make still a remark on the case P is 2. Because that seems a bit open now. Eh? If you take Q not equal to 2, what happens for P is 2? And surprisingly, one has the following. If you take P is 2 and X is LQ, well, LQ with Q bigger than 2, well, I will choose the P later. X is LQ with Q bigger than 2, and I take A to be a diagonal operator like this with lambda k positive and going to infinity, then A has condition H, so LP regularity for P bigger than 2. However, A fails to have maximal, so stochastic maximal L2 regularity, which is, to me, this was really surprising when I realized this. And it's not really difficult to prove. It takes about 1.5 pages. 1.5 pages. But it's kind of surprising. P is 2 is really a limiting case that seems to work only in the Hilbert space framework. And the Banach space framework, you have to go with P bigger than 2. Well, the reason for this actually goes back to the deterministic theory. So L2 is somehow a limiting case, as is L1 or L infinity in the deterministic case. So actually, to prove this, we used the result of Bayon from the 80s and the result of Sylvie de la Brière from 95. And well, it's a nice counterexample. Well, to prove the theorems that I will not explain, that would take me a lot of time to explain it, all our stochastic integration theory goes into the proof of the theorem. But not only that, we need, for instance, Pfefferman-Stein maximal inequalities. We need R-boundedness techniques, if you know what it is. We need the H-infinity calculus, of course. We need also the factorization method of D'Aprato and Kwapin and Sapchik. So there's also plays a role to get the second theorem. We need the factorization method. And we also need trace embeddings. And what is kind of work in progress is to apply this to nonlinear SPDEs. And we also want to consider other Banach spaces than the LQ spaces. But this is also possible. Thank you for your attention.
Are there any questions?
You took the Brownian motion to be one dimensional, but you can take d-dimension Brownian motion as
You
well.
can take a cylindrical Brownian motion.
I think it most of me is the part where you use the stochastic integration in the UMD spaces, because you.
Yeah, so I did not explain the proof.
Yeah, no, but I mean, you take Q larger than 2, but.
Yeah, so that's a good question. I mean, if you take Q larger than 2, then you could try to apply the stochastic integration theory from intermezzo 1. But I tried to show in the beginning of the talk that this does not work. And you have to use the two-sided estimate. because that still contains more information and enough information. That's the thing.
And for the functional calculus, you don't need any assumption on the like UMD property assumption.
Well, here I explained it just on the LQ spaces. But if you go into the literature on H-infinity calculus, you will see that most examples that they have will be on UMD spaces. And as soon as you leave the case of UMD spaces or real interpolation spaces, then it breaks down. So on L1 or the continuous functions, etc., you do not have usually bounded H-infinity calculus.
Which applications to nonlinear equations do you have in mind?
So we try to do it for semi-linear with non-Lipschitz coefficients, because then we could try to apply Sobolev embeddings to get global estimates. And like in the deterministic theory has been done by several authors. But also we want to go in the quasi-linear or the quasi-linear direction, because that seems natural now that you have such an estimate. But still, this is work in progress. I mean, and also, what you can do is try to go in the direction of non-autonomous equations using this technique, like you also have done in the papers with Chris Veraar for the deterministic case. That you also go into the non-autonomous case using maximal regularity techniques. So this is also something we will do here.
In your second intermezzo, you mentioned the fact that you have an Ito formula for the duality LQ prime. What about the Q's norm of Q? Or?
Yeah, but that was already in Brzezinsk's work, or actually Neidhart's work.
Okay.
But you, I mean, to answer your question,
Because
I mean, I understand the question. So we also have an Ito formula for C2 maps on UMD spaces.
trace your Ito correction to be different, because you have hidden to us what this question mark norm is. So I guess that must
No,
be
that's still okay. That's still okay.
It's still okay.
Yeah, but the one problem is that you cannot just take the q'th power of an LP norm if p is smaller than 2, because that function is not 2 times differentiable.
Yeah.
So then you have
In the
problems.
framework where everything is not above 2, it's just the same.
Yeah, but if you take a differentiable function, then it's okay. But if you would stay away from 0 with your function, your process, then it could still be all right, even for the LP norms with p smaller than 2. But that's more technical, of course. That's
So any other? Okay, so let's thank the again.